about metal forming processes. Last week we talked about sheet metals, and we explained what sheet metals are, the types of things that are made or fabricated from the sheet metal. So today we are going to talk about metal forming processes. And in the metal forming processes, we are going to talk about two distinctions. That is, we have two categories, that is the bulk deformation and the sheet metal working. So definition of sheet metal forming processes is a large set of manufacturing process in which the materials are deformed plastically to take a shape of the die geometry. So the tools used for such deformation is called the die, punch, etc. We're going to look at these tools, and we're going to look at how they do the metal forming process. So depending on the type of process. So plastic deformation, what is this plastic deformation? It is the stress beyond yield strength, and we say that the yield strength is the strength beyond which a substance, a metal, or an item can bend. So beyond that yield strength, it breaks. So that is the yield strength. So the stress beyond yield strength of the workpiece material is required. That is the plastic deformation. Now we have two categories of metal forming process, which is a bulk metal forming and sheet metal forming. So I'm going to zoom out this flow diagram so that we can see. So in metal forming process, we break it into two. We have the bulk deformation and we have the sheet metal working. And under the bulk deformation, we have the rolling process, the forging process, the extrusion processes, wire and bar drawing, bending operations, deep or cup drawing, shearing processes, miscellaneous processes, and so on, and then stretching. So the classification, these are the classifications of the metal forming processes. So when we go further now to the classification of the basic bulk forming process, we start with the bulk forming process. We say it's rolling, forging, and extrusion. So we go step by step. Bulk forming process, it is the severe deformation process resulting in the massive shape and change. It really changes the object from its shape to another thing. So you can see now, like an example of the rolling in this picture. This is the workpiece, and when the rollers get into it, you can see the way they are doing the finishing, or the chipping off, the shearing off the unwanted parts, and the way it is changing, totally changing the shape. Now forging is here. Punching, you can see a die, and the workpiece, and then it is being punched so that it can form a different shape. You can see that forging process. And we have the extrusion process. You can see the workpiece, and you can see now the die, or the die that is used to form it, and it is changing its shape totally. Now we have said that the bulk forming is the severe deformation process resulting in massive shape and change. So the surface area to volume of the work is relatively small, mostly done in hot working conditions. The rolling. Now, what is rolling? Rolling is the process. Rolling in this process is the workpiece in the form of slab or plate, and is compressed between the rotating rolls of the in the thickness direction. You can see where it goes, and then so that the thickness is reduced. So the rotating slab, or the rotating piece of the slab, into the gap and is compressed and compresses it. So the final product is the form of a sheet. So it is shown in the first picture. So forging. What happens in the forging process? So in forging, the workpiece is compressed between two dies containing a shaped continuous shape. Shapes are impacted into the final part. And in the extrusion process, in this, the workpiece is compressed. This one here, the workpiece is compressed or pushed into a die, once opening to take a shape of the die hole. So you can see it is being pushed in. It is being pushed in so that it can take the shape. It is taking the shape of the die. The die is in this shape, so it is being forced in. The workpiece is in blue. You can see all the workpieces are in blue. They are being forced in to take the shape of the die. That is the extrusion process. And then the wire and rod drawing is similar to extrusion, except that the workpiece is pulled through the die. So in this case, the workpiece is pulled through the die, but in the extrusion part, the workpiece is forced in. It is forced in to the die. So classification of the basic sheet metal forming. Now we said the sheet metal forming has the bending, the deep drawing, the shearing, and the shearing. So the sheet forming. Now the sheet forming involves forming and cutting operations performed on sheets, strips, coils, and coils. So the surface area to volume ratio of the starting metal is relative. So tools include punch, die that are used to deform the sheets. Bending. What is bending? Bending in this the sheet metal is strained by the punch to give a bend shape, that is the angle, usually a straight axis. The dip or cap drawing, in this operation, forming of a flat metal sheet on a hollow shape like cap is performed by stretching the metal in some regions. So the blank holder clamp and blank on the die while the punch pushes into the sheet metal. And then the shearing. What is the shearing? This is nothing but cutting off sheets by shearing action. By shearing action, you are cutting the sheets. You can see the way it is done. Maybe we have an upper die and the lower, a punch and a die. So when the punch is hit down, it cuts the surface. So that is shearing. Now we have cold working, warm working, and hot working. What is the difference between the two, or what does it mean? Cold working, generally done at room temperature. So that is the cold working, definition of the cold working. It is done at room temperature, meaning without change of any temperature, or slightly above the room temperature, meaning you can heat slightly a bit. So what are the advantages of the advantages compared to hot forming? So there is a difference between hot forming or hot working and cold working, and we're going to look at the warm forming and working and the hot working. So advantages of a cold compared to hot working is it has closer tolerance and can be achieved, and a good surface finish. It has a good surface finish because of strain hardening. It has a higher strength and hardness. It is seen in part, which is seen in part, and 4 is the grain flow during deformation provides the opportunity for desirable directional properties. And again, since number 5, since no heat of the work is involved, the furnace or fuel electricity costs are minimized because it is a cold. We said it is a cold. It's a cold working process, so it does not need any heat. Number 6, the advantages is the machining requirements are minimum, resulting in possibility of near net shape forming. So what are the disadvantages? The disadvantages is it needs a higher forces because you need to take a lot of force, because when you hit a metal, you soften its texture and it becomes softer. So the softer it becomes, the more the work, the more easier the work can be performed. So a disadvantage of this cold working is it needs higher forces and power is required for it to be done. And then the strain hardening of the work metal limit the amount of forming that can be done. And sometimes the cold forming, annealing cold forming cycle should be followed. That is a disadvantage. And then the workpiece is not ductile enough to be cold worked. Now, warm working. What is warm working? In this case, forming is performed at temperature that just above the room temperature, but below the recrystallization temperature. So the working temperature is taken to be 0.3 Tm, where Tm is the melting point of the workpiece. The melting point of the workpiece. So this is a very important point here, that in the in warm working temperature, it normally works at a temperature that is slightly above or just above the room temperature, but below the recrystallization temperature. So what are the advantages of the warm working environment or the warm working metal forming process? In this, the advantages are: number one, it enhances plastic deformation properties. It's enhanced plastic deformation properties. And then number two, it lowers the forces that it lowers the forces. Let me zoom so that we can see required for the formation, to intricate work geometric possibilities. Number four, annealing stages can be reduced. So that is the warm working environment. What about the hot working environment? The hot working environment, it involves deformation above crystallization temperature between 0.5 above the melting point to 0.75 of the melting point. Advantages: the advantages are a significant plastic deformation can be given in the sample. And then number two, the significance change in workpiece. There's a significant change in workpiece because it needs less power, less force. Lower forces are required because when it is working, when it is very hot, working in hot environment, so even the deformation is very fast. Number four, the materials are premature failure cannot be formed. And then absence of strengthening due to work hardening. And then the disadvantages. What are the disadvantages? Disadvantages is a shorter tool life, and then poor surface finish and lower dimensional accuracy. And then four is the sample surface. That is the disadvantage. Now we go to the bulk forming processes, the forging. We explain the forging process. It is the deformation process in which the workpiece is compressed between two dies. The workpiece is compressed between two dies. You can see how it works. We have the upper die and the lower die, and then the workpiece is compressed in between. So that is the forging. Using either impact load or hydraulic load or gradual load to deform it. So it is used to make a variety of high-strength components or automotive, aerospace, and other applications. The components include engine, crankshaft, connecting rods, gears, aircraft, structural components include engine, crankshaft. These are the things that can be formed out of the forging process. Connecting rods, gears, and the engine, the jet engine, turbines, and etc. So the category based on the temperature, that is the warm, cold, warm, and hot forging. Forging can be done when cold, it can be done when warm, and it can be done also when hot, in the hot forging temperature. Category based on the presses. On the presses, we have the impact load, that is the forging hammer, gradual press of the forging press. And categories based on the type of forming. Now we can have an open die for forging, an open die forging like this one, where we have an upper and the open die forging. You can see this one. We have the upper die and the lower die. Impressive die forging, we'll look at them, and the flash forging. These things are very important because they will appear in your exam. You'll be told that give the classifications of the forging, the bulk forging processes. You will now give the categories according to the three categories that we have talked about. We have talked about the categories based on the temperature, that is the cold, warm, and hot. We have talked about the categories based on the presses, that is the impact load pressing, and we also have the gradual press and the forging press. And we also talked about the category on the type of forming. The type of forming, we have the open die, the impressive die, and the flashless die. So in open die forging, the workpiece is compressed between two flat platen, and thus allowing the metal to flow without a restriction in the sideward direction relative to the die surface. The pressive die forging. What happens in the impression die forging? This is what happens in the impression die forging. In impression die forging, the die surfaces contain a shape that is given to the piece during compression, thus restricting the metal flow significantly. So there is extra deformed material outside the die impression, which is called the flash. So this can be trimmed or for further or later. So the impression die forging, you can see that is the die is the upper die is here and the lower die is here, and it is done like a compression. They are being compressed in between, and they take the shape of the die. And this one is normally done when it is the working piece is very hot. You can see when it is very hot, it can take the shape that it needs. And then we have the flash forging. You can see the flash forging. The workpiece is put into, you can see the die, the stationary die is there, which already has a specific shape. And we have a punch. A punch is pushed in to form the piece, the shape that is needed. So in flash forging, the workpiece is fully restricted within the die and no flashes are produced. So the amount of initial workpiece used must be controlled and must be controlled accurately so that it matches the volume of the die cavity. Okay, we have open die for forging. What is now an example of open die forging? We talked about the open die forging having the upper and the lower dies. So the simplest example of open die forging is the compression of the billet between two flat dies, halves, which is like a compression test. This also known as the upsetting or upset forging. Basically, the height decreases and the diameter increases. You see now what is happening here. The height decreases, meaning it is being pressed. It is being pressed using two dies, and the diameter increases because the surface area now, whatever is pushed from above and below, it increases sideways. So under ideal conditions where there is no friction between the billet and the die surface, the homogeneous deformation occurs. So in this, the diameter increases uniformly throughout its height. So in ideal condition, that is the constant there is the ln h naught over the h, that is the height. We will piece, and at the end of the compression be the maximum of the whole forming. Also, the force is equal to that, the not f and then a, and is used to find the force required of the forging, where the d naught f is flowing stress compressed of that stage. So you can see the height, not the diameter there, the vf and the vf1, the height is reduced here. Now the h naught, that is the initial height, that is the next side, that is the partial compression, and the complete formation, that is the complete compression. Now the height, the final height and the final diameter is there. You can see now the diameter is bigger than the initial part and the height is smaller than the initial height. So that is what happens there. So in actual forging process, the deformation will not be homogeneous, and the bulging occurs because of the presence of friction at the die interface. So this friction opposes the movement of the billet at the surface. This is called the barrier effect. The barrier effect will be significant as the diameter or height, that is d over h ratio, of the workpiece increases due to the greater contact area of the billet die interface. And then temperature will also affect the barrel phenomenon. Now look at this. This is now the actual forming process. So the start compression is there, the partial compression, and then the final compression. You can see now this actual forging in accurate force evaluation is done using the F is that formula. K is a constant that is normally given, and it's here, where K is the forging factor, which is a constant coefficient, and that the coefficient of the ratio is given by that, and then the D is the force piece diameter. So at some time it will be needed to do some small calculations. Typically, the load stroke curve, you can see how the forging process, the forging force against the height. So if a certain force is given, the height, so as the force increases, the height also increases. The effect of the D height ratio, the diameter height ratio, is here. The effect and the ratio are given there. The closed die forging. Now, what is the closed die forging? The closed die forging, called as the impression die forging, is performed in dies which has the impression that will be impacted to the workpiece through forming. In the intermediate stage, the initial billet deforms partially, giving the bulge shape. Now, during this die full closure, now you can see now the closed. In the closed, we have the upper part closed, being closed in a certain way, and the lower part also closed in a certain way. So you can see the intermediate shape, and we can see now the final stage with the flash formation. So you can now see, and this one has a flash formation, meaning some material part will go to the flash, meaning will go to the left space outside there. The formula used for open die forging earlier can be used for the closed die, which is the formula is there, where F is the maximum force in operation, A is the projected area of the part, including the flash, and then DF is the flow stress of the material, and KF is the force factor. Now, selecting the proper value of the flow stress is difficult because the strain varies throughout the workpiece for complex shapes, and hence the strength varies. So we have a table here that has it gives the difference K factor of the part and shape that are formed of different formations. So the intensive die forging, we have the simple shapes with flash, we have the K factor to be 6.0, and I said that K is normally a constant that is normally given. And then the complex shapes with flash have 8.0, and the very complex shape having 10.0. So the above equation is applied to find the maximum force during the operation. Since this is the load with that will determine the required capacity, the press used in the forging operation. The impression die forging is not capable of making close tolerance objects. Machining is generally required to achieve the accuracies needed, so the basic geometry of the part is obtained from the forging process. The subsequent machining done on those portions of the part that require precision finishing, like holes, threads, etc. So in order to improve the efficiency of closed die forging, precision or forging was developed that can produce forgings with thin sections, more complex geometries, closer tolerance, and elimination of machining allowance, precision of forging operations. Sometimes machining is fully eliminated, called near net shaping or forging. Flashless forging. Now, when we don't have a flash, how does it look like? Now, 3 stages of flashless forging are shown below. In flashless forging, most important is that workpiece volume must equal the shape in the die cavity within the very close tolerance. So if the starting billet size is too high, the excessive pressure will close the diameter of the die of the press. So if the billet size is too small, the cavity will not be filled because of the demands. So this process is suitable to make simple. It will be used to make simple and symmetrical parts geometries to work materials such as the aluminium, magnesium, and their alloys. Coining is a simple application. Now, what is coining? You can see now the way it's done. It's a simple application of a closed die forging in which fine detailed die work impressions are impressed into the top or the bottom surface of the workpiece. So you can see the dies. We have the punch and the die here, and this is now the starting blank that is being used, and now the coining is here. It is used to make different shapes. You can see the fully compressed, and then the ram pressure. Now it is out, and now you can see how the tool is. Very nice outfit. Now, though there is little flow of metal in coining, the pressures required to reproduce the surface details in the die cavity are at par with other impression forging operations. Now, forging hammers, presses, and dies. Now, these are now drop hammers. These are now how the hammers are being used. The hammers operate by applying an impact loading on workpiece. So this is also called the drop hammer, owing to the means of delivering impact energy. When the upper die strikes the workpiece, the impact energy applied causes the part to take the form of the die cavity. Sometimes several blows of the hammer are required to achieve the desired change in shape. So drop hammers are classified as: number one, we have gravity drop hammers, power drop hammers. Now, gravity drop hammers, what are they? They achieve their energy by falling weight of the heavy ram. So the force of the blow is dependent on the height of the drop of the weight of the ram. So you can see there. Let me zoom out so that we can look at it. So this is the anvil. The ram is there, the piston rod, and the head containing the cylinder. So it is pressed down and it makes shapes on a workpiece that comes. Those is a drop hammer. Gravity drop hammers, they achieve energy by falling weight of heavy ram. So the force of blow dependent on the height drop of the ram. So power drop hammers, they accelerate the ram by pressurizing the air or steam. The presses, the force is given. What about the presses? You can now see how the picture, how it happens when it is being pressed. So you can see the working piece, and when it is pressed, using the difference, the upper die and the lower die, and then the partly. And then we have the mechanical pressing. Now the presses, now the force is given in the forcing by lead gradually, and not like impact forging. And then the mechanical presses. In this press, the rotating motion of the drive motor is converted into the translation motion of the ram. So they operate by means of the eccentrics, cranks, and knuckle joints. The mechanical presses typically achieve high force at the bottom of the forcing stroke. So we have also the hydraulic press, which are using hydraulic pistons. So hydraulic driven piston is used in the actuate the ram. And we also have the screw presses. They apply force on the screw mechanism that drives the vertical. Both screw driven and hydraulic driven operate at relatively low ram speeds. So we have the forging dies. You can now see the way they happen, or the way it takes place. Parting line. The parting line divides the upper die from the lower die. So in other words, it is the plane where two dies have meet. So the section of parting line affects graining flow in the part, required load, and flash formation. Draft. It is the amount of taper given in the sides of the parts required to remove it from the die. We have the draft angle. It is meant for easy removal of part after operation. It is completed at 3 degrees for the aluminum and the magnesium parts, that is 5 degrees at 7 degrees for steel parts. The web and rib, there are thin portions of forging that is parallel and perpendicular in the part line. More difficulty is witnessed in forging parts that as they become thinner. So fillet and corner radii. Small radii limits the metal flow and increases on the die surface during the forging. The flash, the pressure build up because of the flash formation is controlled. Proper design in gutter and flash land. Upset forging. Now you can see now other forging operations. We have upset forging. It's a deformation operation in which the cylindrical workpiece is increased in diameter with reduction in length. In industry practice, it is done as closed die forging. So upset forging is widely used in the fastener industries to form heads on nails, bolts, and similar products. So you can see there the upset forging is widely used in the fastening industries to form heads and nails and bolts and similar products. So you can see now how it can form a head. So a certain shape is given there and it is being pushed in. Now feeding the workpiece, you can see how the workpiece is being fed. Then this is the punch, it is being put there. And then when the punch comes in, it pushes this workpiece and forms the shape. And then it grips. And then when it is pushed in between to finish the space or to gather the space in between, it forms that top surface. So things like nails, bolts are formed using this process. The heading. Now these are the heading. You can now see the exact way that we can now. The following figures show a variety of head operations with different die profiles. You can now see this one. You can now see another one there. You normally see these things that we normally use, the screws and everything that we normally. These are the ways that they are formed. We have head formed inside die only, and then we have the bolt head formed by the die punch. And now the long bar stroke, that is the workpiece, is fed into the machine by horizontal slides. So the stock is upset, forged, and the piece is cut to appropriate length to make the desired product. So the maximum length that can be used, that can be upset in a single blow, is 3 times the diameter of the initial wire stroke. Swagging. Swagging is another way of forming. So swagging is used to reduce the diameter. You realize that we are learning a lot of these things in one setting because they are a necessity. Swagging is used to reduce the diameter of the tube or the rod at the end of the workpiece to create a tampered section. So in general, this process is conducted by means of rotating dies that hammer a workpiece is a radial direction inward to tamper the piece that is fed in the die. So the mandrel is required to control the shape, size of the internal diameter of the tabular parts during swagging. So you can see the swagging part. So the workpiece is here and it is pressed in. You can see these are dies and it forms a shape. It's like the part is sheared. And then the final diameter is here. And then we have the radial forging. Radial forging is when the workpiece is rotating in between the dies. And then this operation is the same as the swagging, except that it is radial forging, because radial meaning it rotates. So the workpiece does not rotate. It's supposed not to rotate around the workpiece. Instead, the workpiece is rotated as it is turning into the armor dies. So the diameter reduction of the workpiece, the tubal tapering, you can see, and then the swagging to form a groove and the tube. When these are now different shapes that are formed out of swagging. Rolling, forging. Roll forging, we are talked about it at the introduction of part, is the forming process used to reduce the cross section of the cylindrical or a rectangular roll by passing it through the set of opposing rolls that have matching grooves, that is with respect to the desired shape of the final part. Now it combines both rolling and forging part classified as forging operation. Now, depending on the amount of deformation, the rolls rotate partially. That is, the roll forged parts are generally stronger and possesses desired grain structure compared to the matching that might be used to produce the same part. We have the orbital forging. Orbital forging, now it rotates in an orbit, so you can see the orbit path. It is being this upper die is being rotated or being tilted. Now you can see it's the process forming that is impacted in the workpiece by means of the cone shaped upper die that is simultaneously rolled and pressed into the work. So the work is supported on the lower die. So because of the inclined axis of the cone, only a small area of the work surface is compressed at any stage of forming. So as the upper die revolves, the area under compression also revolves. Because of the partial deformation contact at any stage of forming, there is a substantial reduction in press load required. You can now see that. Isometric forging, isothermal forging, it is the hot forging operation in which the work is maintained at some elevated temperature during forming. So the forging dies are also maintained at the same elevated temperature. By avoiding chill of the work in contact with the cold die surfaces, the metal flows more readily and the force requirement is reduced. Extrusion. It is the bulk forming process in which the work metal is forced or compressed to flow through the die hole to produce a desired cross-sectional shape. Example, squeezing toothpaste from the toothpaste tube. Advantages. A variety of shapes are possible, especially using hot extrusion. Grain structure and strength properties are enhanced. Cold and warm extrusion. So close tolerance are possible, mainly in cold extrusions. So types of extrusions, we have direct or forward extrusions, in indirect or backward extrusion. Now direct extrusion means is the metal bullet, a metal bullet is first loaded. Now we look at the pictures and see how that is formed. A metal bullet is first loaded into the container having die holes. Now the ram compresses the material, forcing it to flow through the die. So some extra portions of the billet will be present at the end of the process that cannot be extruded and is called the butt. So it is separated from the product by cutting it just beyond the exit. So let us see how that happens. So we can see the direct extrusion. This is the ram and this is the final work shape. So it is being pushed in, and this is the work billet, and the container is here. It's being pushed in and it's being extruded. So direct extrusion, now the significant amount of friction exists between the billet surface and the container walls as the billet is forced to slide towards the opening. So because of the presence of friction, a substantial increase in the force is required. So in hot direct extrusion, the friction problem is increased by the presence of oxide layer on the surface of the billet. This oxide layer can cause defect and defect the extruded product. So in order to address these problems, a diamond block is used between the die and the work billet. So the diameter of the dummy block is kept slightly small than the billet diameter, so that the thin layer of the billet containing the oxide layer is left in the container, leaving the final product free of the oxide. So now you can see how the problem is solved. You can see how the small space as a final workpiece is there, and the mandrel is there, the die and the work billet and the container and the ram. So the making hollow shapes, this one is used to make hollow shapes. You can see it a punch or an inside part is there using the direct extrusion. Hollow shapes like tubes can be made using direct extrusion setup shown in the figure above. So the starting billet is prepared with a hole parallel to its axils. The billet is compressed. The material will flow through the gap between the mandrel and the die opening. In direct extrusion, in this type, the die is mounted on the ram and not the container. As the ram compresses the metal, it flows through the die and the ram inside, which is opposite direction and movement. Now, since there is no relative motion between the billet and the container, limitations: the lower rigidity of the hollow ram, difficulty is in supporting the extruded product at the exit. Now, in direct extrusion, solid billet and hollow billet, you can see there, simple analysis of the extrusion, the pressure distribution and billet dimensions in direct extrusion. Now, assuming the initial billet and the extruded are around the cross-section and are important parameter extrusion, find as below. There are various equations used to evaluate the actual true strain and associated ram pressure during the extrusion. So the following relations proposed by the Johnson is a great interest. So these are formulas that are used to calculate the extrusion strain. The extrusion strain EX and A and B are empirical constants of the given die and angle. So in case a question is asked, you'd be needed to use these formulas in the calculation. So we can see the above equations that are used. Sliding friction. Sliding friction, what is this? It's a column of friction stress, tau, denoted as tau, between two surfaces is proportional to the normal pressure. So the constant or proportionality is called friction coefficient, that is micro, and this is assumed constant, but not mandatory. The condition exists when the forming tools are well lubricated. And we also have the striking friction. These are constants that are used in the calculation. In this condition, a layer of material is contained. The die surface may stick on the plastic floor and may occur just under the surface layer. So that is an example of a question that is given that can be calculated, and this is the calculation. You will go through this at your own time because I've already shared the notes with you. So in case of anything, you will make me know so that we can discuss. Extrusion dies are two important factors in extrusion dies are the die angle and the orifice shape. So for low die angles, the surface area of the die is large, resulting in increased friction at the die billet interface. So the higher friction results in the higher ram force. So for a larger die angle, more turbulence in the material flow is caused by during reduced friction. During reduction, increased ram force required. So those are the calculations. And then materials, we have the hot extrusion, that is the cold, the tool and alloy steels. The important properties of die materials are higher wear resistance, high thermal conductivity to remove the heat from the process. We also have for cold extrusion, we have tool steel and cemented carbides. Carbides are used when a high production rates, that is long die and good dimensional control are expected. So other extrusion processes, we have the impact extrusion. And now I want us to have a break at that point so that we can come back with the other extrusion processes. We are going to participate in the discussion. There are some questions that are posted there in the discussion. So we are going to participate in the discussion for the next 40 minutes. And we will be back here at exactly 10. I think we'll use 50 minutes. We'll be back here at 10. At 10, yes. Let's say at 10. Yes. And after that, we will proceed and finish this part that is left. And then I will tell you what we'll be learning next week. Your results for the cards will be out by the end of this week. So I'm still on with the marking, and you will get your results there. You'll be able to access your results in the portal. So can I hear any metal forming? Yes, just mute your mic. You are still on sheet metal forming. So I want us to just add an overview of what you had in the first session. So examples of things. Now you can see examples of things that are formed out of sheet forming method. We have aeroplanes. You can see the aeroplane bodies. We have tins. We have tools that we use in our daily lives. We have things like the tins there. We have automobile bodies. We have so many things. Any metallic thing, we can see the shapes. The 90 million cars and commercial vehicles produced worldwide out of the metal forming processes. The results of metal forming processes and sheet forming processes. Objectives. By the end of the day, when you are learning this, you should be able to describe the different forming processes, when they might be used, and compare their production rates and the costs. Yes, Grace. Okay. And compare the cost and the environment impact. And then we have to calculate the force predicted parts, defects, tearing, wrinkling, dimensional accuracy, and let me see that word, and propose the solutions, and then explain the current developments. So that is the importance of learning the sheet forming processes. We need to know how to explain the current developments, opportunities, and the challenges that are met in the industry. So you can see the workshop where these things happen, how it works. You can see how busy they are. Look at the first picture, how this processes, the punching, the dies, and forming of the processes are done. You can now see the punch steel, the sheet metal that is being used. You see the way it makes that shape. Those are the metal forming processes. You can see the workshop, now the machines. And remember, we started by learning the machines. The first topic that we were learning is the tools in the workshop and workshop machines. We learned of the workshop machines, shearing machines, punching machines, drilling machines. So these are the machines now at work, and they are used to do the metal forming processes. So materials are drawn into shapes, that is conventional drawing, stamping. They are expensive tooling, not net thinning, quick. You can see the hydroforming, cheap tooling, or not net thinning. Then materials stretch into shape, that is stretch forming and super plastic forming. Stretch forming is very cheap tooling, and net thinning, slow and low formability. And then the super plastic forming is the cheap tooling, and also it's very expensive and sheet forming. So drawing. I remember we left at a point where we were talking about the drawing. We were talking about the drawing, and this drawing, expensive tooling on net thinning. That is a drawing. You can see now a deep drawing is here. So we have a punch there, the drawing force. Drawing force is maybe you can knock with a hammer, you can knock with a heavy thing, or you can even use a machine to push the punch in. That is how, this is a blank holder. This is the blank itself, and the holding. So you can see the blank that is being formed. It is already forming a U-shaped thing. So those are the things that happen. The shallow drawing that is on the surface. can see how it happens. Deep drawing, you can now see the deep drawing, that is the blank holder is there, and the limiting drawing ratio, that is the LDR defined, that is the maximum D over the diameter. Maximum distance, that is the diameter, the big diameter D over the small diameter, that is the drawing reduction. The diameter. You can see now things that are fabricated. These are things that are manufactured and fabricated. We have sinks. We have so many things that are made out of the sheet forming processes. Blank holder forcing forming window. You can see the wrinkle, the tearing window for forming depth and draw. We can see them there. The deep drawing of drink cans. Now look at the way the cans are formed. Now look here. The process of blanking, you can see what happens. The process illustration, that is the punch, stock, and the dice. And then the result, you can see now what is already formed, that is the cross section and the circular thing. The deep drawing, it makes hollow parts. You can see the deep drawing, that is the punch, the blank, the die, and the blank holder. And it's already made that. And we have the redrawing. Redrawing, it's a punch. There's a deep drawn cap and a die there, and you can see how it works. And then we have another one is ironing. Ironing is there, a punching, redrawing, a cap, and then the ironing, a ring, and the die. And then we have a dooming. Dooming is there, punch, iron cap, and die. Then we have necking, a doom can, and support, that is spinning tool. Then we have the seaming tool is there. And then the metal forming process involved in manufacturing a two-piece aluminium. Can have it there. The hydroforming chip tooling, no net thinning, slowish, high formability, low volume batches. So these are things, the outcomes. I'm still showing you the outcomes of this forming process. So hydroforming, you remember we talked about the hydroforming process. The hydroforming process, that is chip tooling, no net thinning, slowish, that is highly formability. These are the outcomes. You can see the things that are made for, during, and after, how it looks like. Another, we are still on hydroforming. You can see the small flex forming tools made by additives or manufactured. And then you can now see also the stretch forming. In the stretch forming, you are stretching it out, meaning the punching machine or the dice is on the below part and it is making that stretch. So it's very cheap tooling and net thinning, slow formability, steel metal up to 15 millimeters by 9 meters. Then the jaws are there, the carriage is there, you can see the press table, and then the form die. So this form die is pushed up so that it can bend this material of the sheet that is being bent. So you can see the wrapping is there, the pre-stretching is there, and then the release. When you release, now what you get. Then the higher aspect ratio of the deeper parts are there. Super plastic forming, that is a cheap tooling made thin, slow, expensive sheet metal, very high formability, low volume badges, that is 0.5 to 0.75 melting point. You can see the temperature at which the superplastic forming is done, that is the blowing pressure of that superplastic material. You can see now it is forming, this is the substance that is being formed, the sealing plate, and then the formation product. So you can see how it has already bent and it has already formed. This is the dice. So it comes in and it melts and forms. You can see the temperature is very high, 500 degrees Celsius, very high temperature. So the formed product is here. It is bent to the form that is needed. Forming of force and parameters and geometry. Tensile test, the stress strain diagram. So we are testing the tensile. Now an object has already been formed. The thickness is there. So we test the force. That is the force measurement. We are measuring if this thing can actually withstand the work that is going to form. So how do we measure? We have some materials or tools that are used to measure the tensile stress and strain. So it is pressed in a way and it is clipped there so that it can be able to withstand that force, so that you can test if it will actually do the work that it's supposed to do. Okay, so the power law expressions of the homology equations, we had already talked about these equations earlier on. Tensile instability necking, how it's calculated, useful assumptions, the 3D of problems. Now when we are using the matrices, and you can see the yield criteria that are there, calculations, sharing, origin of effective strain, forming limit diagrams, strength, stretch forming and forming force needed to bend sheet metal. The bending is there. Those are simple. This is now the sharing that we talked about. Bending force requirements, those are formulas that are used. No doubt these are punch when we are calculating the force and the width of the die open. So that is the force is the LT squared over W, where T is the thickness, sheet thickness. W is the width of the dice, that is the open part. You can see that the width from this part to this part. And then L is the total length of the bend of the page, and then the UTS is the ultimate tensile strength of the material. Note that the notation used in the text, that is LW, differs from that used in the previous description of BL. So we have to be very careful in marking this. So what shape have been created once now the steel versus the aluminium. Now when you're using steel and you're using aluminium, how perfect or how well does the shapes form? So all those, you can see the graphs of the yield, skin, the strength of the spring back. Now note that the R in the figure below is mislabeled, should go to the center line of the sheet. You can see now where the middle, wherever it is bending, that is the R point. Elastic springing back analysis. So the bending moment, the curvature is there. So those are the most important things that we need to know in the metal sheet forming. We have known the processes, we have known the stages. You will need to do just a few calculations, like the one that I gave, the first example that I gave in the first session, in the earlier on session. Methods to reduce the spring back, that is the smaller yield, larger thickness at the over, bending, the stretch forming, coining, and the bottoming the punch. You can see the pure bending is there, the tension, the compression, bending, stretch. Fully plastic is there. Stretching or forming, we can achieve a strain of this. Friction and the Capson equation. So those are the things that I wanted us to look at. The shape control concept. I've already shared so many notes there in the portal. So you guys, you need to download these notes and go through them. Conventional spinning. Now spinning to bring different shapes. And now up to that point, I think today's class is done, and I will expect any questions in case there's a question before we can wind up and finish the class. So that is on metal forming processes. So you can see the strain and the stress. These are now the formulas. This one gives exact formulas. Now the tensile force acting on a rod, the shear stress, how we calculate that, and the formulas, the strain. You need to know all this because they'll be appearing in your exam. The two-dimensional stress analysis and the three-dimensional stress analysis. That is the stress strain analysis, the stress analysis, and the typical. So all these things, you will need to go through them. Yield criteria, you can see how to calculate. Now we have a formulas here and theories. Hot working, you see it is explained there. Cold working, we had talked about it. Strain hardening, and then recovery, we have said that is the strain recovery, the gain growth, regularization, and gain strain. Hot, sometimes you will be told to differentiate, to compare and contrast between the hot rolling and the cold rolling. You should be able to know, like the metal fed is the roll after being heated before the recrystallization temperature, and in the cold, the metal is fed on the roll when it is below the recrystallization temperature. Remember, we talked about them. In general, that in hot, in general, rolled metal does not show work hardening effect. Here, the metal shows the working hardening effect. So those are the things that we need to go through them. You can see the rolling. All these notes are in your portal, so you will be able to get them there. So in case of any question, kindly, you are allowed to ask the types of rolling. You can see them. These ones are detailed notes for you guys. Okay, so I want us to stop there. That is the forging process. I want us to stop there unless there's a question.